Hello and welcome to another session of classical motion of a single particle. We simply discuss some typical problems, actually two very usual situations where we encounter the simple harmonic oscillations. The first one is the most famous one. This is the case of a mass attached to a spring. Okay. So, now you know that spring is such an entity that which is always trying to maintain its original length. When this is in a forced or strained situation, that means someone is trying to make some deformation in its original length, which we sometimes call the length relaxation length or the length of relaxation, okay, or relaxed length L0. If someone tries to deform the spring by just changing its length L0 in two ways, let us say by expanding or by compressing this. So, when this deformation is very weak, then the spring is actually gives a force by virtue of its property called stiffness, okay, which is given by the spring constant K. That gives a force, the spring gives a force which is exactly equal to F is equal to minus Kx x cap direction, where x cap is the direction of the spring. Okay. Now, this is in general true when the deformation is weak, and then we say the spring is within the so called elastic limit. Spring is within the elastic limit, where Hooke's law is valid. If Hooke's law is not valid, then of course, a linear I mean a force linear to the displacement is not expected. Okay. If I have this, and then I can actually say this is the most usual and most complete example, although very simple, but very complete example of a simple harmonic oscillation. Most usually what happens that you have a rigid wall and a spring is actually attached to this, and someone is actually either pulling this or pushing this in this direction. Then this is the force you encounter if this direction is the x direction. Okay. Now, of course, you should write this Ax is nothing but its final length minus its relaxed length. That you also sometimes have to use in while solving problems, because we give you L0 and then we give you L, then you have to actually subtract the L0 from L to get this x, and finally, you should write this m x double dot will be equal to minus K L minus L0. That is the correct way to think. Okay. Now, another point is, okay, so this is a famous example. Another point which is very popular example of simple harmonic oscillator, and actually if you just talk to a person who is not really working in the domain of physics, but somehow interested in the natural phenomena, and if you just say somehow he or she has some basic knowledge about physics in a very school level, and if you say that where you can see the simple harmonic oscillation, the first example he or she would use is the example of a pendulum. And in general you will see that the spring definition is given by mostly the physicists or the engineers, but people who are amateur in this field, they do not use the springs example very often, they give the pendulums example, and that is why I took this as a second one, but I will somehow advise you to use this example as a caution because of two reasons which I will come in a while. Okay. So, the pendulums example is very simple, is that there is a rigid ceiling type of thing, and you have a string which is attached to this ceiling, and at the end of the string there is a point mass m which is hanging, okay, vertically, and there is no other disturbances at this moment on this pendulum. Now, someone just took the pendulum a little bit, and the assumption is, and then the bob or the small mass point comes here. The assumption is on the string is that the string should be massless and the string is also inextensible. So, that means if I just take the bob over here, the string length will not change. Okay. So, if this is L, this should be L. So, it will actually expected to describe a circle, imaginary circle over here with radius L. Okay. If we do that, then if this angle theta is very small, then again for this theta we will have a simple harmonic oscillation. That is true. But why we have to take caution for this, I am coming to that point. Okay. So, just I am trying to first solve the dynamics of this equation, and that is actually a very actually a complementary topic which is actually needed to be discussed in this discussions on when we are discussing on the central force motions. So, you will see that is very interesting, that when the bob is here, the bob is acted upon by several forces. One is the tension force, another is the weight of the bob, which is mg vertically downwards. Okay. Now, since the mg is vertically downward, you can actually have two components. One is radially outward direction for the bob, and the another component which will be this tangentially cross radial component. Okay. Radially, so this angle is theta, because this angle is theta. So, radially you have mg cos theta, and cross radially the tangentially will be mg sin theta. Now, you see when you just release the bob, just pulling a little bit over here, then the bob will come back to this position because of this component of the force. Okay. And once again you have to think that if I now cast this whole thing as a motion in 2D plane, because if I mean we just think of a very simple case of a pendulum, then the pendulum actually moves in a plane, and that plane, for example, this is the plane of this paper here, and we assume for the sake of simplicity there is no movement outside or inside of the plane of the paper. Okay. So, if we have this, then we can use our 2D plane polar coordinate system to analyze the motion, and we can again write m r double dot minus r theta dot square will be equal to its radial component of force, and for the cross radial component we will have m r theta double dot plus 2 r dot theta dot, which will give me f of theta. Correct. So, here since what is this r and theta? So, simply you now think that r is the distance, instantaneous distance of the bob from this center, which is this origin O I can name, and theta will be right from this reference direction, which is vertically downward. Theta will be any angle which is calculated anti-clockwise. So, if theta is calculated anti-clockwise, it will be positive, if clockwise it will be negative. Okay. So, I can actually write for this case, since L is not changing, actually my R is constant, and that constant is exactly equal to L, and that is why this is 0, this is 0. So, my final equations will be m minus m L theta dot square will be equal to, now what is Fr? Fr is the resultant force acting on the particle in the radial direction, and that is nothing but, so this is the radial direction outward. So, that means this is the direction, this has the direction of positive r cap. So, that is radially outward from O. So, that is why I will write what are the forces acting over here. One is mg cos theta radially outward, another is T, the tension of the string, that is radially inward. So, I can write mg cos theta minus T for this, and from this one I can write m L theta double dot will be equal to, so this is 0, this is 0 and this is 0, yeah, theta double dot will be equal to f theta, which is mg sin theta. Now, this I said that theta cap dot, I mean theta cap direction is the direction of increasing theta in the anticlockwise direction. Now, when it is coming back, so it is actually in the negative theta cap direction, so that is why there will be a minus sign. Now, you see that when this equation is approximated for a very small value of theta, this sin theta comes to be theta almost. So, for theta tends to 0, sin theta tends to theta, and then your ml theta double dot becomes minus mg theta almost. And then you can say that my theta double dot is actually almost g by L theta with a minus sign, and you have theta double dot plus g by L theta, which is equal to 0. It looks like an equation for theta, where theta is expected to execute simple harmonic oscillation. But remember, first of all, this is not in general true for arbitrary theta. It is only true when the theta is very small, tending to 0. And another thing is that this is not, even for small theta, this is not a simple harmonic oscillator in displacement, but it is for the theta, that is the angular displacement. Okay. And final point, what is very important here for the readers or for the students, is that this is not a central force situation at all. So, if we try to think this as a central force, okay, as an extension of the central force, like let us say where F is equal to minus kr, and from that I just do that the analysis of the simple harmonic oscillations, then this case is not that. This case is a highly non-central force, and that you can easily see because it has a force which is directed along the theta direction or the theta cap direction. Okay. That is why I am saying, although this second example is very popular, but the physicists have to use this very carefully. Once again, this example is much more complete. This example is interesting, but you have to take caution, and it is not actually a case of a central force. Okay. Thank you.